Hello, Tao. Okay, I can see you. Can you hear me?
Yes, I can hear you.
Okay. Sounds is very low in your side.
Hello, is better now?
Maybe you can increase the volume or something because you seems very far.
Okay, is it better now?
Yeah, it's good.
Okay, change it. No idea how to change it. You alright now? You think?
Yeah, I think it's correct. Okay.
Right now, so everything alright? The recording working now?
So welcome everybody to this webinar. Thanks again for Tao to do this presentation for IIFC webinar. The title of the presentation is Behavior and Modeling of Fiber Reinforced Polymer Confined Concrete. And Tao is associate professor in Wollongong University in Australia. So I think it's quite late for him today. Thanks again to be here. And so, Tao, when you want to start, feel free to do it. Thanks again.
Yes, today I'm going to talk about the behavior and the modeling of FRP-Confined concrete. So I will first have a brief introduction of the research background of the FRP-Confined concrete. Then I will move to the theoretical modeling part, which includes three categories of models: design-oriented models, analysis-oriented models, and three-dimensional constitutive models. So we all know that FRP has become more and more popular in the past 2 decades as a strengthening material for concrete structures. FRP can be used on the bottom of a beam for fracture strengthening, on the side of a beam for shear strengthening. It can also be wrapped around the column to enhance both the load capacity and the ductility of the column. In the last case, the concrete is confined by an FRP jacket or an FRP wrap. And such concrete is the topic of today's talk. Of course, FRP has been widely used because of their many advantages. This includes their high strength to weight ratio, which means the lifting equipment in many cases can be eliminated. It also means labor cost can be reduced. That's split in shape. The fiber strips can normally be handled in rows, and it's easy for wrapping on curved surfaces and around columns. And last but not least, the tailorability in mechanical properties. And this means that the mechanical properties of FRP concrete can be designed by placing the fibers in different directions according to a certain stepping sequence. And for example, for confining purpose, the FRP can be designed to have only resistance in the hook direction. So this avoids the problem of potential buckling because of excessive axial stresses. Now let's move to the behavior of FRP-confined concrete columns. Let's start with the failure move. We know that when concrete is under compression, it expands laterally. And in an FRP-confined concrete column, such lateral expansion is constrained by the FRP. Consequently, the FRP is subjected to hook tension. So when the hook tensile strain of FRP reaches its rupture strain, FRP ruptures. And that is the failure mode of most FRP-strengthened concrete columns. For circular columns, such rupture can happen anywhere around the circumference because of the symmetric nature of the column. But for rectangular or square columns, such failure normally happens at one of the corners, which is the most critical region in such columns. This slide further explains the stress gates of concrete in a circular column. So basically, it said when concrete is under extra compression, its lateral expansion is restrained by FRP, which provides lateral confining pressure to the concrete. Consequently, the concrete is under triaxial compression in all the three directions. And if we cut half of the FRP jacket as an isolated body, FRP jacket is subject to the reaction force from the concrete, which is delta R, and this delta R has to be balanced by the tensile stress in the FRP jacket, as you can see from the right figure. So actually, if you write down the force equilibrium equation for this isolated body, that will be the basis of most theoretical models for FRP-confined concrete. This slide shows you the actual stress strain curve of unconfined and confined concrete. So this short blue curve is for unconfined concrete with a strength of 40 megapascals. So you can see it's basically a very brittle material. When it reaches its peak stress, the stress decreases vertically. And this long red curve is for FRP-confined concrete. So you can see both the strength and deformation capacity of concrete can be much enhanced when it's confined by FRP. And you may also notice that the curve of FRP-confined concrete features a bilinear shape. This is different from the black curve, which represents the curve for steel-confined concrete. For steel-confined concrete, normally you have an ascending branch, then followed by a descending branch. So why is the difference? It's because the confining material, steel and FRP, they have quite different material properties. For steel-confined concrete, when the steel is under hook tension, it very quickly reaches yielding. And after the yielding of steel, it provides a constant confining pressure to concrete. However, for FRP-confined concrete, because FRP is a linear elastic material, so the confining pressure provided by the FRP continuously increasing with the lateral expansion of concrete, which means for concrete confined by FRP, the confining pressure is always increasing with the deformation. So this difference in the material properties of the confining material leads to the difference in the behavior of confined concrete, as you can see from the left figure. So just now we know that the failure of FRP-confined concrete column is normally controlled by the rupture of FRP. So in order to determine the ultimate condition, the question is, what is the rupture strain of FRP? The most straightforward way to find the answer is to do a material test, such as the Fred-Coupon test specified by the ASTM standard. However, existing studies have found out that the rupture strain formed from a FRP-confined concrete column is normally much lower than the rupture strain that can be formed from the material test, such as the Fred-Coupon test. And this table summarizes some test results. But you can see from this column, which represents the ratio of the rupture strain in a confined column with the rupture strain in material test. So basically, in the column, only say 6% to 85% of the material strength can be used. And this is an important conclusion for the design of such strengthened column. The reason for this difference in the rupture strain can be various. For example, it can be because of the non-uniform deformation of the concrete, can be the curvature of FRP jacket in a circular column or near the corners of a square column, can be because of the multi-axial state of stress in FRP jacket. We know that in the material test, FRP is under one-dimensional loading only, but in a FRP-confined concrete column, the FRP is under hook tension plus axial compression. So this may affect the rupture strain in the eruption. And other possible reasons include the local misalignment of fibers or residual strains and the probability of weakness in the fibers itself. Now, with this in mind, let's move to the modeling part. And before I talk about the models, let's first clarify the definition of some terms, which will be very often used in the presentation of the modeling part. The first term is actively confined concrete, and in this presentation, this refers to concrete confined by constant confining pressure only. FRP confined concrete, so unless otherwise specified, it refers in this presentation to concrete in a circular column confined by an FRP package, which means the concrete is under uniform confinement from the FRP. And the third term is concrete under triaxial compression. It refers to concrete subjected to equal principal stresses in two lateral direction and a principal stress in the axial direction. The last term is concrete under biaxial compression, and this refers to concrete subject to equal stresses in two principal directions and a zero stress in the third principal direction. Let's keep this in mind. Now, at the beginning of the presentation, we said there are three types of models. Now, let's first look at the first one, which is design-oriented models. So from the name, you know that these models are developed for design purpose. They are basically one-dimensional model. This means they predict only the actual stress-strain curve of the concrete. They tell you nothing about the lateral extension of concrete. They are normally in closed form expressions so that they are easy for design use. So we know that for this kind of models, they are generally developed based on the regression analysis of experimental data. And they are expressed in closed form equations. So whether such kind of models are reliable or accurate depend on whether the expressions you choose, the form of expressions you choose, can represent the shape of the curve. That's the first thing. The second thing is whether your tested base is large enough. That's the second thing. And thirdly, whether the parameters you choose in the equations can represent the behavior of the concrete. And these are the key issues we need to consider when we develop such kind of design models. Now let's first look at the first thing, which is the form of expressions. Except the form of expressions should represent the shape of the curve. And this equation, which was initially proposed by Sargent in 1970s, has been widely used by a number of researchers in their design-oriented models. So this is a two-parameter equation. It looks complicated, but if you choose wisely the value for this A and B, you can end up with a bilinear curve, which is similar to what you get from the test. So this is one type of equation we have been using. And some other researchers also use this equation, which is the four-parameter equation. And the advantage of this equation is that each parameters in this equation, they have very clear physical meaning. For example, this E represents the elastic modulus of concrete, and this EP represents the second stage stiffness, and this FO represents the intercept with the stress axis, and this M controls the transition zone. But you may notice that these equations feel very complicated in form, probably because these models, they tend to use one simple equation to represent this two-stage curves. And the third type of model is the very well-known Lemon-Tans model. A Lemon-Tans model basically they use two separate equations to describe the two different stages of FRP-confined concrete. This model consists of a parabolic first portion and a linear second portion. These two portions are smoothly connected together. So one of the most important advantages of Lemon-Tank model is that it can reduce to the model for unconfined concrete, which is adopted by the European standard. So in this way, actually, both unconfined concrete and FRP-confined concrete, they can be covered by one unified model. And this is one of the most important advantages. And because in this model, they use two separate equations to describe two stages of the curve. The equation is also much simpler than the other equations. So basically, it's a parabolic equation for the first stage, as you can see here, and it's a linear second equation. And of course, you need to define some important parameters such as the strength for the connection point of these two stages, and also the stiffness of the second linear stage. Another important point is the ultimate point. In Lemon-Tank model, this equation is used to define the strength of confined concrete, which is FCC time. So this FCC is linearly related to the confined pressure. So the confined strength of concrete is linearly related to the confined pressure, and they choose the parameter 3.3, which based on their test database fits best with the test data. And if you are familiar with the steel confined concrete, you may notice that this parameter, this factor 3.3, is much lower than some famous model for steel confined concrete. For example, in Richard's model in 1908, he used a factor of 4.1 for steel confined concrete. So just keep this in mind, and later on I will explain a little bit why this is the case for FRP-confined concrete. While for FRP-confined concrete we use a lower factor. And this equation is for the ultimate axial strength. So it's not a linear function. It's related not only to the confining pressure at L, but also related to the hook rupture strength of FRP. If you want to know more details of how this model is developed, please refer to Lemon-Tank paper published in 2003. And this is the performance of this model. You can see the predicted test results very well for the strength and the axial strength. And for the axial strength in curves. So just now, the Lemon-Tank model, the original model was proposed for FRP-confined circular columns. For FRP-confined rectangular columns, it's a different story. Firstly, because in rectangular columns, you can imagine that the concrete is under non-uniform confinement, and the confinement is less effective. And normally, before we apply the FRP wrap, we need to make the right angle corners run. This figure explains the mechanism of a concrete in a rectangular column. So we know that when concrete is under compression, it expands laterally. But for this type of concrete, when it expands laterally, it's constrained by this side FRP. So it's different from the case in a circular column. In a circular column, we know that because of the pressure from the concrete, the hook jacket is independent. However, in a rectangular column, the side FRP is under bending because of the lateral expansion of concrete. If you do some simple calculation, you will find out the bending stiffness of a twin wall jacket is much less than the tensile stiffness of a jacket with the same thickness. which means the confining stiffness in a rectangular column is much smaller than that in a circular column. And in other words, the confinement is less effective in rectangular column. So existing stress field models for rectangular columns, they basically use the concept of effective confinement area. They believe that this part of concrete, which is close to the side, is not effectively confined because there's very small bending stiffness of the side jet. However, the confining pressure that concrete receives from the corner of the FRP jacket is much larger. So that there's a so-called effective confinement area in rectangular columns. And for the stress field model developed based on this concept, such as Lemon 10th model, in their another paper published again in 2003, they used two reduction factors, one for the strength, one for the ultimate axial strain, simply because the FRP confinement is less effective. So the compressive strength needs to be reduced compared with their circular column counterpart. And the same for the ultimate axial strain. And Lemon 10th model was developed around 12 years ago. And now there are some recent advances of this model. In 2009, they published a refined version of the design model for circular columns. And in this refined version, they basically provide some more accurate predictions for FRP-confined concrete with a relatively weak FRP jacket. And more recently, I worked together with Professor Tan's group. We developed a design on this model for concrete under confined FRP steel confinement. And this is the case for FRP strengthened reinforced concrete column. For that kind of column, because the concrete is not only under confinement from the FRP jacket, but also under confinement from the steel stirrup. So that is a combined confinement. So we have developed a new model based on the original version proposed by Lemon 10 in 2003. And this model works particularly well for confined FRP steel confinement. Alright, that's the first category, which is design-oriented. Now let's move to the analysis-oriented model. So just now we said design models, they're basically one-dimensional model, but analysis models, they're typically quasi-two-dimensional. This means an analysis-oriented model, it not only predicts the axial stress, axial strain behavior, it also predicts the lateral expansion behavior of the concrete. But most of the existing analysis models, they work only for uniformly confined concrete, which means concrete in a circular column. Before we can understand analysis-oriented models, let's have a further look at the experimental curves. So in this figure, we're plotting the normalized stress strain curve of FRP confined concrete and actively confined concrete. To recall, we define active confined concrete to be concrete with a constant pressure. So we have a group of thin curves here. Each curve, they represent concrete confined by a certain constant pressure. So you can imagine that the lower curve is for concrete with a lower pressure, but the higher curve is for concrete with a larger confinement pressure. But for each of these curves, the confinement pressure is constant during the loading process. And this thicker curve is for FRP confined concrete. But we know for FRP confined concrete, the confining pressure continuously increases with the deformation, which means for each point on this curve of FRP confined concrete, the confining pressure is different. Alright, keep this in mind. And experimental results tell us when this curve intersects with one of the curves for actively confined concrete, for example, this curve, this intersecting point. At this intersection point, existing test results revealed that at this intersection point, the confining pressure provided by the FRP jacket is almost the same as that for from the active confined concrete, which means it doesn't matter whether it's an FRP confined concrete or actively confined concrete. For the same strain, axial strain, and stress, the confining pressure is always the same. And this is one important observation which forms the basis of most analysis-oriented models. And if you take a further look at this intersection point, you may notice that the intersection point may not necessarily be the peak point, which is this point, of an actively confined concrete. So the intersection point is normally lower than the peak point of actively confined concrete. So this explains why for FRP confined concrete, in the design model, we choose a factor of 3.3, which is lower than the normal factor in an actively confined concrete. For example, 4.1 in Rita's model. Alright, and this figure shows you the axial strain, lateral strain behavior of, again, a group of actively confined concrete and FRP confined concrete. Alright? So this thicker curve is for FRP confined concrete, and this dotted curve are for a group of actively confined concrete with different constant confining pressure. Again, you can see that there are a number of intersection points, and existing test results revealed that at intersection points, confining pressure from the FRP jacket is the same as the confining pressure of this actively confined concrete. Which means at the intersection point, it doesn't matter where you receive the confinement from. Confining pressure is always the same. This is another important observation, which is the basis of most analysis-oriented models. Alright, with this in mind, this is how most analysis-oriented models works. The first step is for a given axial strain of concrete to find the corresponding lateral strain according to the lateral to axial strain relationship. Which means for one given axial strain, we need to have one equation to find lateral to axial strain relationship. And because of this observation shown in the top figure here, you can expect that this equation must work well for both actively confined concrete and concrete. This is the first step. So we find the lateral strain from an axis. And the second step is to find the confining pressure from the lateral strain. And this can be done based on force equilibrium, as we talked about at the beginning of this presentation. If you take half of the FRP jacket as an isolated body, if you write down the force equilibrium equation, you can find out the relationship between the hook strain of FRP and the confining pressure of concrete. And this part is easy to do. And third part, if you have done the first two steps, so you already know the confining pressure and the axial strain, right? So if you know the confining pressure and the axial strain, you can use any existing model for actively confined concrete to find axial stress. Which means if you know the confining pressure and axial strain, you can predict all of this group of curves for actively confined concrete. Alright? And because we said at the intersection point, both FRP confined concrete and actively confined concrete have the same axial stress and strain, then that means you can determine one point on FRP confined concrete. In In this way, we find one axial stress from one axial strain. So we determine one point on the FRP-confined concrete. If you repeat this process, you find a lot of points on the FRP-confined concrete so that you can find the whole curve. So just now we know that this is the general procedure for most analysis on this model, and in particular for the model proposed by Tao Yu in 2007, what they use is this equation for the lateral to axial strain relationship. But we said this equation not only works for axially confined concrete, but also works for FRP confined concrete. And for the second step, they use this force equilibrium to find the relationship between the hook strain in the FRP and confined pressure. And for the third step, we said we need a model for actively confined concrete. So in test model, they choose the very well-known model developed by Mendes group in 1988. So with this three key components, test model can predict very well the axial stress strain curve of FRP confined concrete and the lateral expansion curve. Now let's talk about the last category of models, which is three-dimensional constitutive models. These models are very often used in finite element models, and it can not only be used for uniformly confined concrete, which is in circular column, it also can be used for non-uniformly confined concrete, such as the concrete in rectangular column or in other shape columns. If you do a quick review of all the models for use for confined concrete, you may notice that most of these models can be categorized to be two types. One is the so-called plasticity models, and another one is the so-called plastic damage models. And both of these models involve concrete plasticity. So we'll talk about concrete plasticity first. And this table summarizes some existing models which have used concrete plasticity. And all these models, they use the so-called DP type plasticity model. And we will focus on this type of plasticity model first. And the conclusion which we will find from this type of models can also be applied to other types of concrete plasticity models. And these DP type models, they are widely used, they're simple, they involve only two parameters, and they can capture the important features of confined concrete, which is the shear strength increases as a result of hydrostatic pressure increases. We will talk more about this later. So, for concrete plasticity models, if you look at the key components of it, basically there are three key components. First one is yield criteria. Second one is hardening rule or softening rule. And third one is the flow rule. Let's look at it one by one. So if you try to write down all the equations for the three-dimensional constitutive models for concrete, this is just part of it. You will feel it's too complicated, right? But today, we'll not talk about the derivation of mathematical equations. We'll talk about principles behind these equations. Hopefully, this can provide you a better understanding of how this works. And if you understand the basic principles behind these equations, in my view, it also helps you if you want to derive these equations. Let's look at the yield criterion first. Just now we said in a DP type model, it can reflect the increase of shear strength with the hydrostatic pressure increase. and that is reflected in this two-parameter function for yield criterion. Basically, the yield criterion is a function of J2, which is the second divatoric stress invariant, and I1, which is the first stress invariant or hydrostatic pressure. So basically, in the meridian plane of the stress space, this function is a straight line in the plane, which means the shear strength increase with the hydrostatic pressure. So this is different from the well-known Fourier criterion for metal. For metal, the J2 is a constant for most metals such as steel. However, for concrete, J2 increase with the hydrostatic pressure at a certain rate. So as you know, in this function, the two parameters, one is theta, one is k. We need to define these two parameters. For theta, it defines the slope of this straight line, right? If you recall, the confined strength of concrete is a linear function of confining pressure. This is also a linear function. And this J2 is a combination of this confined strength, which is in the axial direction, and this confined pressure, which is in the lateral direction. The J2 is the combination of these two stresses. And at the same time, I1 is also a combination of these two stresses. So you can imagine that we can find this theta from this factor of this linear function, 4.1. This is also what most studies have done. So if you want to know the more details, you can refer to my paper published in 2010. But basically, the idea is we find this theta from this factor, 4.1. If a different factor, you get a different theta value. And for the k value, it's basically the intercept with the vertical axis. So if you imagine it's a function of the concrete strength. So for concrete with different strengths, you will have a different k. So again, for more details, please refer to my paper. Now let's have a look at what most existing studies have done. So many of them have directly used the original dp yield function, which we showed you in the last slide. However, there are a few studies that suggest that that equation is not enough. For accurate prediction, you will have to include the third divatoric stress. So now let's see whether this is right or not. If you look at the divatoric plane of the stress space, then the dp yield criterion, it can be represented by a full circle. Okay? Because the J2 value is the same in this divatoric plane. If you look at these different stress paths, we assume this stress path is for concrete under biaxial compression, and concrete under triaxial compression will follow this stress path, right? So by using dp yield criterion, we are implying that the J2 value for biaxial compression is the same as the J2 value for triaxial compression. It's the implication of the dp yield criterion. However, based on the test results, we know that the J2 value for concrete under biaxial compression is normally much lower than that for concrete under triaxial compression, which means dp yield criterion, if you just calculate the theta value according to triaxial compression, you will overestimate the result for biaxial compression. If you calculate 6 value according to results from 5 shock compressions, then it will underestimate the prediction for tri-shock compression. So you can never make both of these two cases right. You use the original DP yield criteria. And for concrete under non-uniform confinement, it's somewhere in between. Alright? This curve. So if you cannot make the two extreme cases right, you cannot predict right the concrete under non-uniform confinement. Okay? So in order to address this issue, what we need to do is to use a non-linear shape for the yield surface in the divided state. And this means the third divided stress invariant should be included. That's why some of the existing studies they have done this, and that makes sense. Alright, that's about the first thing, which is yield criteria. Now let's look at the hardening rule. Okay, for the hardening rule, the first question is whether you include hardening rule or not. In most existing studies, for this question, the answer is yes. They use hardening rule. But a few studies, they didn't include hardening rule. We'll see whether this makes sense or whether this makes sense for some particular conditions. And for the research which have used a hardening rule, some of them use associative hardening rule, some of them use some of them relate hardening rule to the confining pressure. Some of them didn't relate the hardening rule to confining pressure. We'll see which one makes sense. So on the right hand side, we have some equations depicting the hardening rule. Basically, if you use K as a function of the plastic deformation and make the K change with the plastic strain, then this represents the hardening rule. And in most models, people use the equivalent plastic strain to describe the overall plastic deformation of the material. And the equivalent plastic strain can be defined by these two equations. So if a model does not include a hardening rule, means the model is an elastic perfectly plastic model. So apparently, for unconfined concrete, if you use a perfectly plastic model, it doesn't work, which means hardening and softening rule has to be included. However, some studies, they argue that even though the perfect plastic assumption does not work for unconfined concrete, it can work for FRP-confined concrete. Let's see whether this makes sense or not. Look at this figure. We have seen this before. It's the axial stress strain curve of a group of actively confined concrete and FRP-confined concrete. And we also said that the intersection point of these curves, they are not necessarily the peak point of actively confined concrete. They're normally lower than the peak point. If you take the perfectly plastic assumption, that means up to the peak point, the stress remains constant. Alright? But in real case, for FRP-confined concrete, the stress is lower than the peak point, which means if you simply take the perfect plastic assumption, you get all the other components of your model right, you still overestimate the performance of FRP-confined concrete. So the answer to this assumption is no. You cannot use that to predict where the performance of FRP-confined concrete. Only when your FRP-confined concrete is with a very steep FRP jacket, which makes the slope of the second stage very close to this dotted curve, then your model may provide reasonable assumptions, but reasonable predictions, but not accurate predictions. That's the first thing. Now, if a model considers the Hartmann rule, but they use the Hartmann rule as simply a function of the plastic deformation, what will happen is shown in this figure. If the Hartmann rule is only a function of the plastic deformation, then basically you predict parallel descending blocks for concrete under different confining pressure. Okay? If the Hartmann rule is only a function of the constant pressure, is only a function of the plastic deformation, then the descending branches are basically parallel. However, from the test result, we know that if you have a higher confining pressure, then the descending branch is more smooth. If you have no confinement, it's much more stiff. So, apparently, this does not reflect the experimental observation, which means if you use the plastic deformation as the only parameter in your Hartmann rule, it doesn't work. And to fix this, you need to make the Hartmann rule a function also of the confining pressure. You need to include confining pressure in the function. And this shows you if you use both the confining pressure and the plastic strain in the Hartmann rule, you can predict very well the axial stressing curve of actually confined concrete. But keep in mind that only for actually confined concrete. Question is, if you use the Hartmann rule correctly, whether you can predict very well FRP confined concrete. Unfortunately, the answer is no. If we look again, this figure, to find the axial stress based on the axial strain and confining pressure only solves the problem of actually confined concrete. And this is Hartmann rule. To get the confining pressure right in the first phase, you need to predict the lateral expansion of concrete correctly first. And to predict accurately the lateral expansion of concrete, we need to get flow rule right. Right? So if you get Hartmann rule right, you can make sure your model works for actually confined concrete. But for FRP confined concrete, you will have to make sure your flow rule is right, because the confining pressure depends on lateral expansion. Now let's have a look at why flow rule is important for determining the lateral expansion. So in a plasticity model, the flow rule basically defines the direction of the plastic deformation. Right? Like in this case, if you use associated flow rule, then the direction of the plastic deformation is perpendicular to the tangential direction. And the direction of this plastic deformation, as you can find, this overall plastic deformation, they can be resolved into the plastic deformation in two directions. One is the lateral direction, another one is in the axial direction. So the direction of this overall plastic deformation, it depends on the ratio of your axial deformation to the lateral deformation. Right? So if you define the angle of this overall plastic deformation, basically you define the lateral deformation, the ratio of the lateral deformation to the axial deformation. So that's why the flow rule is important for determining the lateral strain at a certain axial strain. Alright, now let's have a look at what existing studies have done. Some of them use associated flow rule, some of them use non-associated flow rule, and some of them further relate the flow rule to the confining pressure. Let's examine it one by one. These are equations for the flow rule. You don't have to understand everything now, just look at the function. Basically, this function defines the flow rule. It's similar to the yield criterion, except that we have a parameter beta instead of parameter theta. Okay? If this beta is equal to the theta, it means an associated flow rule. If the beta is different from theta, then it's a non-associated flow rule. Okay? If you use an associated flow rule to predict the behavior of concrete, and this is what you will get. So this curve is what you will get. Basically, you end up with a much larger lateral expansion than what you get from the experimental test. Okay? So you can imagine if you overestimate the lateral expansion, it consequently overestimates the confining pressure provided by the FRP. So at the end, your actual stressing curve of FRP-confined concrete will be overestimated. So non-associated flow rule does not work. Sorry, associated flow rule does not work, and you need to use non-associated flow rule. Then for the non-associated flow rule, there's a question of how to define this beta. Some researchers, they propose to use a zero direction angle. They claim that if you use a direction angle which is equal to zero, which means beta equal to zero, it works. Let's see whether this makes sense or not. First, let's have a look at the actual stressing curve it predicts for two different types of FRP-confined concrete. One type is for weakly confined concrete. One is for the strongly confined concrete. So for concrete which is confined by a strong FRP jacket, the experimental dilation angle ranges from around positive 5 degrees to negative 4 degrees. And for this case, you can imagine if you take the direction angle equal to zero, it may work, right? Like in this case. However, for weakly confined concrete, when the direction angle is always larger than 0 degree, then if you still use the 0 degree direction angle, what will happen is that you end up with underestimate the performance of FRP-confined concrete, because you're underestimating the lateral expansion, so that you're underestimating the confining pressure. And for this test results, if you use a trial and error process, you may end up with a good prediction if you use a constant direction angle of 8 degrees. So this tells us if you use a constant direction angle, it doesn't work for all the cases of FRP-confined concrete. It may work for some cases. And for different FRP jackets, you may need to use different direction angles. Okay, that's the first thing. The second thing is some existing studies, they choose to use the flow rule which is dependent on the confining pressure, and they base their model on the model of actively confined concrete. And this figure explains that this treatment doesn't work, because as you can see from this figure, the curve for FRP-confined concrete is intersects with the curve for actively confined concrete at a certain point, right? And at this point, we said that the lateral confining pressure is the same. However, the tangential direction of these two curves are quite different. Okay? So the actively confined concrete, they basically have a larger slope at the intersection point. If your model is based on an actively confined concrete test result, then it will overestimate direction angle for an FRP-Confined concrete, right? Because the flow rule determines the tangential direction, not the secant direction of the plastic deformation. And this figure further shows you what's the consequence if you use this kind of model, which is confined pressure dependent. Basically, except because you are overestimating the lateral deformation, you are overestimating the actual stretching curve. Alright, now let's have a summary. There are three components of a plasticity model. For the yield criterion, we said that the original DC model doesn't work. We have to include the third dilatoric stress invariant. That's for the yield criterion. For the flow rule, the associated flow rule doesn't work. The flow rule has to be non-associated flow rule. It has to be related to both the confined pressure and the incremental ratio between the confined pressure and the lateral strength. If you ignore the last part, it doesn't work, as we have shown before. And for Hudson rule, it has to be confined pressure dependent. That is all the necessary modification we need to make for a plasticity model. And if you make these modifications, this figure shows you can predict very well the test result of actively confined concrete, not only for the actual stretching curve, but also for the lateral extension. You can also predict very well the stretching curve and the lateral extension of FRP-Confined concrete. Alright, that's for the first type, which is plasticity model. We just mentioned that we have another type, which is plastic damage model. So you may wonder, the plasticity model already works very well. Why you need plastic damage model? To explain this, we need to have a look at the behavior of concrete. So this is one typical stretching curve of concrete. If you unload the concrete from one point on the descending branch, it will fall apart like this. So you can see that you will have some kind of permanent deformation, which is plastic deformation. And also you have the degradation of the elastic modulus, right? So basically, for this kind of concrete nonlinear behavior, the plastic model can only predict the plastic deformation. It cannot predict the reduction in the elastic modulus. And to predict the reduction in the elastic modulus, you need to use damage the elasticity model. And actually, for concrete non-linearity, people either use plasticity model or damage the elasticity model. So recently, people have started to use confined model with confined plasticity and damage elasticity, and that comes to the plastic damage model. Right, here we just use the model in actors as an example. This is the so-called concrete damage plasticity model in actors. So besides the three key components for plasticity models, there's one additional component which is damage variable, defined by this equation. So based on the similar concept, we need to make some modifications of the CPPN model in actors. So for the plasticity part, we just do the same for what we did for plasticity model. And for the damage component, we make it confined pressure dependent. Another important thing is how to define the effective confining pressure. Because we said that both the flow rule and the hardening rule are confinement pressure dependent. However, for concrete under non-unit confinement, the lateral pressure in two directions, they are not equal. So how to define a unit confinement pressure for those cases is a challenge. So in 2010, we proposed this equation for effective confinement pressure. And the purpose of defining this is for good prediction of the deformation of non-uniformly confined concrete. And we developed this equation based on existing test results of biaxial compression. As we explained just now, biaxial compression is one extreme case of non-uniform confinement. So we think that if you can predict the performance of concrete under biaxial compression, then we can predict one extreme point for this kind of concrete. If we can capture both biaxial compression and triaxial compression, then we capture two extreme points. So if this is good, then we can expect we have reasonably good prediction for non-uniformly confined concrete, which sits between these two extreme cases. And this is the performance of our model for concrete in this column. So this is the so-called double skin column with an FRP tube outside, a steel tube inside. So you can imagine this annual concrete section is under different confining pressure from the outer FRP tube and inner steel tube, so that the confining pressure is non-uniform across the radius. So for this kind of non-uniformly confined concrete, with all these modifications to the plastic damage model, we can now predict very well both the actual stressing curve and the lateral stress. And this is the predictions for FRP-confined concrete in square columns. Again, the predictions are very reasonable. Not only that, the beauty of the finite element model is that we can predict the stress distribution over the cross section. So this is the case for FRP-confined square columns. So you can see the stress distribution. Green one represents higher axial stress, and the blue one represents extremely high axial stress, and the red one represents low axial stress. So interestingly, if you look at this pattern, very similar to what people have assumed for effective confinement error, which means this assumption used in many design models that makes sense. And this also offers the opportunity for us to further refine or improve the performance of this design models based on these more sophisticated finite element models. So because of time, I only have a brief discussion of the two types of constitutive models. So if you are interested to know more details, you can find my two papers published in Engineering Structures in 2010. Alright, that's all for my presentation. Thank you very much for your attention.
Thank you very much, Tao, for the time you spent on this very nice presentation, very interesting. And so I would like to thank you again in the name of IIFC. Thanks again and see you soon. Bye.
So for organizing this, thank you. Bye.
Thank you very much.